So the first three examples, uh, there was a left endpoint and a right endpoint to the set of real numbers that we were describing with interval notation. In the next five examples, right, there's either not a left endpoint or a right endpoint. And so these are called unbounded or infinite intervals. Okay. And so in this fourth example, right, in our graph of our set of real numbers, we have an open circle on the number 1, and then everything is shaded to the right of 1. Okay. So this is a graph of all real numbers strictly greater than plus 1. Okay. So open circle right from high school means you don't include the number. Right? But in interval notation, instead of an open circle, what do we use? Parentheses. And since the open circle is on the left interval in the graph of the set of real numbers, we use the left parentheses to shade everything to the right. So in interval notation, right, the first number, we have a left parentheses, okay, there's an open circle, left parentheses on the left end. So we have a left parentheses, and the first number in the interval is 1. And since there's no maximum number, okay, we use this infinity symbol to represent there's no maximum number. And infinity symbols, both plus infinity and minus infinity, are always enclosed with a parentheses, never a bracket. Because an infinity is not a number. It's just a representation. So this is interval notation for all real numbers greater than 1. Right? We're not including 1, but this is everything greater than 1. And positive infinity, that is the symbol that we use to represent no maximum number. Okay, so there's no maximum number in this symbol. All right, any questions on that? Okay. Now in the fourth or fifth example, instead of an open circle at 1, we have a closed circle. And so that means we're including the number 1. And so instead of a closed circle, we use the closed circle's on the left end. So we replace the closed circle on the left end with a left bracket. And so in interval notation, this is actually all real numbers greater than or equal to 1. I didn't want to write out greater than or equal to, takes too much time. All real numbers greater than or equal to 1. So in interval notation, it's left bracket 1, comma, infinity, because there's no maximum number in this set. Any questions on that? So then in in the sixth example, we have all real numbers less than 2 in our set. So we have an open circle on 2, and everything shaded to the left. Right, this is strictly less than 2. And so in place of the open circle on the right end, we have a right parentheses, and everything shaded to the left. So there's no minimum number in our set. So in interval notation, what goes in the first location is minus infinity. Minus infinity is what we use to represent no minimum number. And then on the right end of our interval, that goes up to 2. And since we're not including 2, we enclose it with a right parentheses. And so minus, right, that's a symbol for minus infinity or negative infinity. You can say it either way, negative infinity or minus infinity. And negative infinity means no minimum number in the set. Okay? So that's all real numbers less than 2 in interval notation. And then the 7th one, you should see the pattern now, right? The 7th one, right, we have a closed circle on 2. So the closed circle on the right end gets replaced with a right bracket. And so in interval notation, set of all real numbers less than or equal to 2 is parentheses minus infinity, 2 right bracket. Again, I'm going to remind you, infinity plus infinity and negative infinity are never enclosed with a bracket, always in parentheses. It's not a real number, it's a representation. And then this is how we write all real numbers, right? Every real number on the real number line is in the set, so the real numbers go from minus infinity to plus infinity. I mean, right? There's no minimum number, and there's no maximum number. Negative infinity, positive infinity get enclosed with parentheses. Okay? So in your web assignment homework, when I release it, you'll get plenty of practice writing in interval notation. So any questions on that? Okay. So let's solve some inequalities. And the solution set to our inequalities will be written in interval notation. So in this first example, we're going to solve the inequality for the variable x. We're going to write the solution in interval notation. So we're going to find all the real numbers that we can put in for x on the left side and right hand side, so that the value of the left hand side is strictly greater than the value of the right hand side. We're going to find all the real numbers we can put in for x on the left and the right hand side to satisfy that inequality. Okay. So this first example is an example of what we call a linear inequality. And so to find the solution set, right, we're basically going to solve for x. And in the linear inequality, solve for x is similar to solving the linear equation for x. Right? So if instead of the greater than sign, we have equal to x plus 3, right? That's a linear equation, and I'm confident, right, you're in pre-calculus, you know how to solve a linear equation for the variable x, okay? And that's basically what we're gonna do here. We're gonna do the same steps as you would with the equation, okay, in solving the inequality. So there are several different ways, several different first steps you could take in solving this inequality for x. What would a young freshman do as a first step?
Negative 5/6 to 6x.
Okay, so you would distribute minus 5/6 inside the parentheses. Okay, and so remember you got to multiply both terms by minus 5/6, right? Remember the distributive property. If I have 5 times x plus 3, or this is a binomial, when I distribute the 5, I got to multiply both those terms by 5, right? So I have 5 times x plus 5 times 3, right, which is 15. So when we distribute the minus 5/6, right, this is a binomial inside the parentheses, I have minus 5/6 times 6x minus 5/6 times negative 30, and that's greater than x plus 3, right? I'm throwing in extra steps. Okay. Well, multiplication undoes division, right? So multiplying by 6 undoes the division by 6. So the 6's cancel, and we're left with minus 5x. In this term, we have negative times a negative, which is positive. And then 5 times 30 is 150, divided by 6 is 25. Now these are the kind of numbers you can expect to see on quizzes and exams, right? You should be able to do this multiplication without a calculator. Okay. All right, so this is greater than x plus 3. What would you do next? Solving this problem. Don't be bashful.
Get the variables on one side.
Yeah, get all the x's on one side, right? So we'll move the plus x on the right-hand side to the left-hand side by subtraction, right? And so minus 5x minus x is minus 6x. Right, so I subtract x from both sides, okay? And now you can see where this is going. Now we subtract 25 from both sides. And we have minus 6x is 25 minus 25 is 0. So we have minus 6x is greater than 3 minus 25, which is negative 22. And now to isolate the x on the left-hand side, I got to divide both sides by negative 6, right? Division undoes multiplication. We have minus 6x divided by minus 6 on the left, and minus 22 divided by minus 6 on the right. What do I got to do? We're dividing both sides by a negative number, so we got to flip the inequality symbol, right? We got to flip. We got to go from greater than to less than. And so on the left, the minus 6's cancel. We're left with x. And on the right-hand side, negative or negative is positive. And you got to be able to reduce fractions as well, okay? And the common factor of 22 and 6 is 2. So you divide the numerator by 2, you get 11. Divide 6 by 2, you get 3. So the solution set to our original problem is x less than 11/3. You put in any real number less than 11/3 in for x on the left and right hand side, and the value of the left hand side will be greater than the value of the right hand side. So this is the solution set and inequality notation. Okay. There are inequality symbols in our solution set, so it's inequality notation. So graphically, our solution set, like here's 0 on the real number line, 11/3 is to the right of it, and so x is strictly less than 11/3, so we have an open circle on 11/3, and then everything shaded to the left. Right? That's the graph of our solution set. Okay? Well, you know, with interval notation, we replace the circle on the right end with a right parentheses and shade everything to the left. Okay? So in our solution set, there's no minimum number. So in interval notation, we have left parentheses minus infinity, right? Because there's no minimum number. And then in the second position goes 11/3, right? Because our solution set is all real numbers up to 11/3, not including 11/3, enclosed with the right parentheses, because they're not including 11/3. And so this is the solution set in interval notation. And that's the final answer. Okay. Because you're instructed to write solution in interval notation. Okay. Any questions on that? All right. On the next page, we're going to solve what is called a combined inequality. Where are you? So we have -3 is strictly less than 7 minus 2x over 3 is less than or equal to 4. Okay. So this is a combined inequality, and it's actually two inequalities in one. Okay. The first inequality is -3 is less than 7 minus 2x over 3. And the second inequality is 7 minus 2x over 3 is less than or equal to 4. Okay. So, in solving this combined inequality, right, what we have here are two linear inequalities. And so one way of solving this combined inequality would be to solve this first linear inequality, find its solution set. Then solve the second linear inequality, find its solution set. And then find all the values of x that are in both solution sets. And the values of x that are in both solution sets are in the solution to this combined inequality, or the solution to this combined inequality. Okay. So, in our solution set, the values of x satisfy both inequalities. That's that's why we have the word and here. Okay? Because this is minus 3 is less than 7 minus 2x over 3, and 7 minus 2x over 3 is less than or equal to 4. Okay? All right. But we don't have to solve two linear inequalities and then find the values of x that are common to both solution sets. We can solve this directly. Okay. And so in performing mathematical operations on a combined inequality, whatever you do, right, there are three sides to this thing, right? There's the left side, the middle, and the right side. So whatever you do on the left, the middle, or the right side, you have to do to all three sides, okay? Not just one. So we're going to solve for x in the middle, okay? And here we got division, 7 minus 2x, right? Fraction bars are like division symbols. 7 minus 2x divided by 3. So to get rid of the 3 in the denominator, we have to multiply all three sides by 3. Okay? So we have minus 3 times 3 on the left is less than 3 times 7 minus 2x over 3 in the middle, which is less than or equal to 3 times 4 on the right. So I multiply all three sides, the left, the middle, and the right, by 3. Well, on the left, minus 3 times 3 is negative 9. And then in the middle, multiplying by 3 cancels the division by 3. And we're just left with 7 minus 2x. And on the right, 3 times 4 is 12. I've continued to isolate the x in the middle. We can subtract 7 from all three sides. We have minus 7 on the left, minus 7 in the middle, minus 7 on the right. Minus 9 minus 7 is negative 16. 7 minus 7 in the middle is 0. So we're left with minus 2x in the middle. And then on the right we have 12 minus 7, which is 5. Alright. So now to isolate the x in the middle, you have to divide all three sides by negative 2, right? Division undoes multiplication. So we have minus 16 divided by negative 2 on the left, minus 2x divided by minus 2 in the middle, 5 divided by minus 2 on the right. So since I'm dividing all three sides by a negative number, what do I got to do? Yeah, flip the inequality symbols, right? So less than gets flipped to greater than, less than or equal to gets flipped to greater than or equal to, right? So now I got to simplify. Negative over negative is positive. 16 over 2 is 8. In the middle, negative 2's cancel, and we're left with x. And on the right, 5 divided by negative 2 can be written as minus 5x. Okay, I can pull the minus sign out front of the fraction. Okay. All right. So when dealing with a combined inequality, having the inequality symbols saying greater than instead of less than is kind of awkward. Okay, so we can rewrite this. Students sometimes have a hard time seeing this, so I'm going to give you an example with real numbers. Okay, you know that 8 is greater than 5 which is greater than 2, right? It's all true, right? So if I flip that over, put the 2 over here, leave the 5 in the middle, and 8 here, right? 2 is less than 5, which is less than 8. So you can take this inequality, you can flip it over, okay? And read it as 2 is less than 5, which is less than 8. So we're going to take this inequality, and we're going to flip it over. Read it as minus 5 halves is less than or equal to x, which is less than 8. Okay. And now we can graph that solution set. Okay. So here's the real number line. Right, we're graphing the solution set for the variable x. And so any real number greater than or equal to minus 5 halves and strictly less than 8, put in for x up here, okay? The middle, the value of the middle will be strictly greater than -3 and less than or equal to 4, okay? So here's minus 5 halves on the real number line. Here's plus 8, and x is greater than, so let's write that out. Our solution set, we can write this as x is greater than or equal to minus 5 halves, and x is less than 8. That's what that's telling us, right? X is greater than or equal to minus 5 halves, and x is less than 8. So minus 5 halves is in our solution set, so we put a closed circle on it. 8 is not, so we put an open circle on it and shade everything in between. Okay, that's how you did it in high school. Okay. Well, with interval notation, we replace the closed circle on the left end with a left bracket. We replace the open circle on the right end with a right parentheses and connect everything. So replacing closed circles and open circles with brackets and parentheses helps you to write the solution set in interval notation. Right? So in interval notation, we have left bracket, and the first number is minus 5 halves in the interval. And then everything up to 8, not including 8. And so we enclose the 8 with a right parentheses. So this is the solution set in interval notation. This is the solution set in inequality notation. Any questions on that? Okay. All right, so let's talk about union of sets and intersection of sets. The union of two sets A and B, we use this symbol right here, right? Looks like the letter U, U for union. Okay. The union of two sets A and B, written A union B, is the set of all elements that are in either set A or in set B. So you have two sets, and you just combine all the elements to get the union of the two sets. So as an example, and A is equal to the set consisting of the numbers 1, 2, 3, 4, and 5. And B is the set consisting of the numbers 3, 4, 5, 6, and 7. Okay. And so to find the set A union B, we just combine all the elements of A with the elements of B. Okay. And so A union B is the set of numbers 1, 2, 3, 4, 5 from A, with the numbers 3, 4, 5, 6, 7 from B. But we've already written out 3, 4, and 5, so we just add 6 and 7. When we're solving problems, we have to write the solution interval notation. Often we have two intervals of numbers that we have to join together with the union symbol. Okay. So any questions on that? Okay. The intersection of the two sets A and B is written with this notation, right? So for the intersection, we just use the upside down U. Okay. This is A intersects B. And the intersection of two sets consists of all the elements that are in both set A and set B. Okay. So in our example over here, the intersection of sets A and B consists of all the elements that are in both A and B. So 1 is not in B, so it's not in this set. 2 is not in B, so it's not in this set. But 3, 4, and 5, the numbers 3, 4, 5, are in both sets A and B. So 3, 4, and 5 is in the set A intersect B. And 6 and 7, two numbers in B, are not in A. Okay? So 6 and 7 are not in the intersection. So the union, you join the numbers from both sets, and in the intersection, you only take the numbers that are common to both sets. Okay? Any questions on that? All right. So the exercise down below, you're given the graph of a function. Okay. Now you might want to put arrows at the top here and the top here. Some graphings, online graphing software is hard. It won't let you put arrows on it. So this actually goes up forever here on the left. It goes up forever there on the left. Okay. This is the x-axis. That's the y-axis. So let's see if I can quickly reproduce that graph. And the shape of this function is reminiscent of a what? It looks like a parabola, doesn't it? Yeah. All right. So here's the x-axis. Here's the y-axis. And y values and function values are the same. Okay? Y equals f of x. That's what that means. Y values and function values are the same. So here's the origin. And so here is what 1 minus 3. So here's minus 1, minus 2, minus 3. Here's plus 1. And that's all I need, I guess. Let's say around minus 1 is where the bottom is. So this is just a crude reproduction. Don't hold me responsible for not being exact. So here's x equals 1. Here's x equals minus 3. Okay. So that's what I was trying to tell you, right? This is the x-axis. This is the y-axis, right? Y values and function values are the same. And the graph goes up forever on the right and up forever on the left. Okay. All right. So we have to use this graph of this function, okay, to solve the inequality f of x is greater than 0. Okay. So what we're going to find, what it's asking, is for what values of x is f of x greater than 0. Okay? For what values of x is f of x above the x-axis. Okay. So you know on the coordinate plane, okay, to the right of the origin, right, the values of x are positive, right, and to the left of the origin, the values of x are negative. Well, on the y-axis, the vertical axis, the positive values of y are above the origin, and the negative values of y are below the origin. Okay. So when we're asking to find the values of x, where f of x is greater than 0, since function values and y values, right, or function values and y values are the same, well, y values are the y coordinates of the points on the graph. Okay. So you're asking for what values of x are the y coordinates positive. Okay. Well, here at minus, to the left of -3, all these points on the graph to the left of x equals -3 have a positive y coordinate, don't they? Okay. So the value of the function is greater than 0. Right? The y coordinate is positive, then the value of the function is positive. Okay. And so we're interested in for what values of x are the y coordinates strictly greater than 0. Right? The function values are strictly greater than 0. So you could almost put an open circle here, because at x equals -3, what's the y coordinate at x equals -3 where the graph crosses the x-axis? 0, right? It's called an x-intercept, right? And where the graph crosses the x-axis, the y value is 0. The function value is 0. Okay? So all the values to the left of x equals -3, all the y coordinates are positive. Function values are positive. Right? So this graph goes up forever on the left end. So there's no minimum x value, right? Out here at x equals -100, the graph of the function is way up here somewhere. Okay. So for this first part, there's no minimum x coordinate, okay, with a positive y coordinate. Okay, all the y coordinates for x less than -3 are positive. Okay. So there's no minimum x coordinate for x value. Okay. But at up to, and that's true for all x coordinates or x values up to -3, but not including -3. So this is an interval of values of x, or an interval of x coordinates. All the x coordinates on this graph less than -3 have a corresponding positive y coordinate, or positive function value. Okay. Similarly, to the right of x equals 1, all the y coordinates are positive, right? Above the x-axis, right? So all the function values are positive. Okay. And we can put an open circle there at x equals 1, because at x equals 1 we have an x-intercept where the graph crosses the x-axis, and the y coordinate or the function value is 0. So for all values of x greater than 1, or all x coordinates greater than 1, the y coordinates are positive, greater than 0, right? Because the graph is above the x-axis. The function values are positive. So this, for the graph greater than, for x greater than 1, we write that in interval notation, left parentheses, 1, comma, infinity. Okay? Then And remember, these are values of x. These are the x coordinates that we're interested in. Okay? And so we have two intervals of numbers where the function values are greater than 0. The y coordinates are positive, okay? Greater than 0. And so to join those two intervals together, we use the union symbol. So this is the solution to this first part of the question. Okay? For what x coordinates, for values of x, are the function values greater than 0, strictly positive? So this is the solution in interval notation. All right, in part B, we're sort of doing the opposite, right? We want to know for what values of x, or for what x coordinates, are the y coordinates or function values less than or equal to 0. Okay. And so, for the second part, okay, we're looking for on the graph where the graph is on or below the x-axis. Okay. Where the graph is below the x-axis, the function values are less than 0. And where the graph crosses the x-axis, the function values equal 0. And so we're interested where the function values are less than 0 and where they're equal to 0. Well, where the function values are below the x-axis, that occurs from x equals -3 to x equals 1. All these points on the graph below the x-axis here, they have an x coordinate, or they have a y coordinate that is negative. Okay? So to write those x coordinates from -3 to 1 inclusive, we use left bracket -3, comma 1, right bracket. Okay. So those are all the x coordinates or x values where the graph is below the x-axis. Okay? The function values are less than or equal to 0. So this is the solution for the second part in interval notation. Okay. Any questions on that? All right. So in the next two inequalities that we're going to solve, they're called polynomial inequalities. And we have to, in solving those, we have to use what I call the test point method. Some students call it the table method because I provide you a table. So in this first example of solving a polynomial inequality, I lay out all the steps for you. Now you don't get all the steps on the exam, but I'm laying out all the exam steps now so you can learn how to solve these things. Okay, and do the homework. So we have the polynomial inequality, 5x squared minus 3x is less than 14. And this is actually also going to be called a quadratic inequality. Okay. So I lay out the steps. The first step, so we're going to find all the real numbers that we can put in for x so that the value to the left-hand side is less than 14. Okay, that's what we're going to do. Okay. But we can't just solve it like we did with a linear inequality. Okay. So step number one, we write the expression so the inequality is greater than 0 or less than 0. So we can get 0 on the right-hand side by subtracting 14 from both sides. We have 5x squared minus 3x minus 14 is less than 0. This is what's called an equivalent inequality. Okay? The solution to this inequality is the solution to our original inequality. Okay? So solving this guy will give us the solution to this guy. Okay? Step number 2 is find all the values of x for which the left-hand side is equal to 0. And we're going to use those values to partition the real number line. Okay? So we set the left-hand side equal to 0. And we got to solve for x. Okay? Now, one way to solve for x is factoring. What's another way you can solve for x? Quadratic formula, right? But fortunately, hopefully you can factor this, but if you can't, you can always use the quadratic formula. Okay? So this factors into 5x plus 7 times x minus 2. And now we have a product of two. This is why it's called factoring. We have a product of two factors. Okay? And if the product of two factors is equal to 0, one of the factors has to equal 0. Okay? This is called the zero product property. So either the first factor, 5x plus 7, is equal to 0, or the second factor, x minus 2, is equal to 0. Okay? So we're still on step 2. This is called the zero product property. And now we solve those two. Those are two linear equations. When we solve the first one, we get x is equal to minus 7/5. When we solve the second one, we get x equals 2. Okay. So those are the two values of x that make the polynomial or quadratic on the left-hand side equal to 0. Okay. So in step 3, we use those two numbers to partition the real number line into intervals. Okay. And the reason I call this the test point method is that we know whether minus 7/5 and whether plus 2 is in the solution set. What we don't know is about these other numbers. Are any of them in the solution set? And so what we can do is we can do a test point from each of these 3 intervals. And if the test point in, say, this first interval satisfies the inequality, then all the numbers in that interval satisfy the inequality. Okay? We don't have to test every number, just one number from each of the intervals. Okay? That's what this is all about. All right, now, minus 7/5 and plus 2 make the left-hand side here equal to 0. Well, our inequality is strictly less than 0. So minus 7/5 and plus 2 are not in our solution set, because if we put in minus 7/5 in for x, the left-hand side is equal to 0, not less than 0. Okay. And that's same as for plus 2. So I'm going to put 2 open circle minus 7/5, and open circle plus 2 to indicate those two numbers are not in our solution set. Okay? And now we're going to do the test point method for each of those 3 intervals. Okay? And out of the goodness of my heart, I provided you with a table. And so we have three intervals. The first interval has no minimum number. It goes from minus infinity to minus 7/5. And these are always open intervals, never closed. There's never a bracket, because we already know the answer for minus 7/5 and 2. The second interval goes from minus 7/5 to plus 2. And the third interval goes from 2 to plus infinity, because there's no maximum number. Okay. So for each of these intervals, we select a value of x as a test point, and then we use it to determine whether it makes the left-hand side up here greater than 0 or less than 0. Okay. One of those two things will happen. So in my first interval, minus infinity to minus 7/5, you can use any number. Try to use a number that is easy to work with. I use minus 2. And so when I put in minus 2 in for x, I have minus 5, I have 5 times minus 2 squared times minus 3 times minus 2 minus 14. And when I do that arithmetic, you should be able to do that arithmetic on an exam, okay? This is equal to 12. Now what's important is not the magnitude of the number. What's important is whether it's positive or negative. And plus 12, right? 12 is a positive number. So every number in the less than minus 7/5 put in for x over here will make the left-hand side greater than 0. Right? Because positive numbers are greater than 0. So the numbers in that first interval don't work. Okay. In the second interval, from minus 7/2 to 2, that contains the number 0. 0 makes a good test point. And so when I put 0 in for x, at 5 times 0 squared, minus 3 times 0 minus 14, which is just equal to minus 14. That's a negative number, right? So what that tells me, any real number greater than minus 7/5 and less than 2, put in for x over here on the left-hand side, will make the left-hand side less than 0. Because negative numbers are less than 0. Okay. So these numbers work. Numbers between minus 7/5 and 2 work. And then lastly, we have the all real numbers greater than 2, right? 3 is greater than 2, so I use that as my test point. And so when I put in 3 in for x, I have 5 times 3 squared minus 3 times 3 minus 14 is equal to plus 22. '22 is a positive number. So that tells me if I put any number greater than 2 in for x on the left-hand side, the value of the left-hand side here would be greater than 0. So those numbers don't work. So the only numbers that work in our inequality are numbers between minus 7/2 and plus 2. So in step 5, the solution set, right, in interval notation, is all real numbers greater than minus 7/5 and less than 2. don't stress if you're, struggling with this. This is how you learn. Okay. So you'll get lots of practice with the assigned homework. Okay. And we're going to be doing this all semester long, so it's important that you understand how to do this. Students often think we're going to do something once and then that's the end of it. No. Math is cumulative. Okay. You're going to be doing this all semester long. It's going to keep popping up in different forms, right? Different problems we'll solve. We'll be solving a problem and it's like, oh crud, we gotta solve an inequality. So we gotta do the test point method or table method, whatever you want to call it. Okay. All right. So on the next page is another polynomial inequality, which we will solve. But I need to take attendance, so because this is the beginning of the semester, I got to keep the administration happy. So we would do this problem first thing tomorrow. Okay, but I need to take attendance. All right. So, for those of you who just enrolled, how we do this is I call you by I'm just going by first names for now until we get to Sam's or to Mary's. And just raise your hand and say here, okay? And for those of you who corrected me with the pronunciation of your name yesterday, hopefully I won't mess it up, okay? This one's spelled, is it Lara?
It's Laura.
Laura,
Yeah.
like just a Laura, pronounced the same way?
Yeah.
Okay. Kate, Sam, Madeline.
Here.
Where you at, Madeline? It is Madeline, right?
Yes.
Okay. Dallas. Anders. Sophie.
Yeah.
Sophie Troy.
Yeah. That's
Okay. Kirsten DeCamp. Grace.
here.
Is it Nevea? Navia?
Nevia.
Say it again.
It's Nevia.
Nevia. Jake.
Right here.
Bronwyn Fisher. Aaliyah. Where you at, Aaliyah? Mia. Joe.
Right here.
Brianna. William James. Enzo. Annabelle.
Here.
Alex. Lyon. Cole. Gordon McMillan. Kayla. Hayden. Claudia. Angelica,
Here.
Melissa, Diego, Hannah. It's amazing that we have so many students in there and no two people have the same first name. Haley, Jeffrey, Oliver, Amaya, all right, very good. I will see you guys tomorrow. Have a good day.
The family jacket. The family jacket.
She has bronchitis. Yeah, that's hers. I'm pretty sure, maybe. She said her teacher had COVID though. I don't know if she was part of it. Well, maybe I'll see. Dude, you're pretty honest.